Hi, in this video we have the sixth chapter to be outlined for business decision models, and it is transportation and assignment models. This chapter introduces the solution methods for transportation models and assignment models, and in this video we'll have a quick look at these models and their solution methods. A transportation problem is a linear optimization problem where the transportation costs are minimized under some constraints. Transportation costs are the costs of shipments from a number of origins to a number of destinations. The constraints are the amounts to be sent to every single destination. Decision variables of a transportation problem are the amounts to be shipped on each origin-destination pairs and denoted by Xij. Here, the general form of a transportation model is given in this blue frame. An inverse pair of a model is called the dual of the primal model. The values of decision variables of the dual model reveal the prices for the constraints of the original problem. This interpretation provides an economic perspective for solving the primal problem. For a transportation problem, modified distribution method facilitates this interpretation. Modified distribution method is used to solve a balanced transportation model. In a balanced transportation model, the supply and demand constraints are equalities and the total supply is equal to total demand. Modified distribution method uses a specialized transportation table for computational convenience. Here we have an example transportation table. Here on the left, at the first column, we have the origin locations, and the amounts of the supplies of these origins are given at the last column. Here at the top, we have destinations. In the first row, these are destinations, and the demands for these destinations are given in the last row, in this bottom line of this table. Here in the bold frame, there are some boxes, and in these boxes, there are decision variables, the transportation amount from an origin to a destination. These are the decision variables. Here we also have smaller boxes in these boxes that includes the cost of transportation from an origin to a destination. The solution method begins with determining the initial solution. There are many ways to initialize a transportation problem. However, in this presentation, we'll look into the three of them, which are northwest corner method, least cost method, and Vogel's approximation method. Northwest method assigns the highest possible value to the box at the northwest corner, the one at the upper right hand side on the table. The value of the assignment is the smallest one of the respective supply and demand. This process iterates until there is nothing left to assign at the last row. Here on the right, we have an expression. This is the basic feasible solution, and these are the values of decision variables obtained by the northwest corner method from the table at the left, and the objective value of this basic feasible solution is 165,000. Least cost method assigns the highest possible value to the box that has the lowest transportation cost. The value of the assignment is the smallest one of the respective supply and demand. This process iterates until there is nothing left to assign. Here we have a set of tables. The least cost method starts off with the one on the left at the bottom. Here, this is our first initial table, transportation table. Now here we'll look for the lowest transportation cost, and it is 0. There are 3 boxes that have 0 transportation cost. So the selection is arbitrary. We can select any of them. In this example, we select the one in the middle, this box. For this box, now we look at the supply and demand values. Between these two, the demand is smaller one with the value of 200. So the assignment here is 200. By assigning this value to the last column, we fully met the demand for the fourth destination, the fourth column. So we paint the fourth column in gray. This is not to be considered in the next phase of evaluation assignment of the assignment. We don't since we fully met the demand for this column, there is nothing to be assigned for the other boxes. So this one is out of consideration for this table. Now again, we look for the lowest transportation cost, and it is 45 for this box. Now we look at the corresponding demand and supply values, which are 1,200 and 800. 800 is the smaller one, so the assignment here is 800. By this assignment, the supply for the first row is fully diminished, so we cannot assign any numbers in the next phase for these two boxes. That means we must paint in gray, and this one is out of concern for the next phase. This row is not to be considered for the next phase. In the third table, the process is the same. The assignment is in here, and so on. At the last table, now we have at the last table, the one on the right at the bottom, we have all the assignments. So this is our initial basic feasible solution obtained by the least cost method. And the values of decision variables are given in this expression on the right. And the objective value of this initial basic feasible solution is 164,000. Vogel's method uses the concept of the penalty costs. Penalty costs are calculated for each rows and columns. Penalty cost is the difference of two transportation costs that are smaller than the others at the same column or at the same row. Vogel's method first determines the highest penalty cost and its corresponding row or corresponding column, then assigns the highest possible value to the box with the lowest transportation cost at the determined column or at the determined row. This process iterates until all the assignments are done. Here again we have a set of tables in here. We start off with this one. For this table, the penalty costs are calculated. For the columns, the penalty costs are written down under the demand values in here. And for the rows, the penalty costs are calculated and written down at the right hand side of this table to the right of the supply values. For instance, for the first row, the penalty cost is 45. This one is obtained by looking for the two smallest values transportation costs on this row, and these are 0 and 45. The difference between them is 45, so the penalty cost for the first row is 45. Similarly, for the first column, the penalty cost is 5. We look for the smallest ones, the two smallest one of these transportation costs, and they are 45 and 50. The difference between them yields 5. So the penalty cost for the first column is 5. Out of these penalty costs, we look for the highest one, and the highest one is 85. So we pick up the third column in here. So the assignment will be on this column. We look for the smallest value of transportation costs, and it's 50. It is for the box at the bottom of this column. So the assignment will be in here. Now we'll look at the demand and supply values. Between these two, 600 and 400. 400 is the smaller one. So the assignment here is 400. By assigning this value, the The demand for the third column, for the third destination, is fully met. So this column must be painted in gray and must be out of concern for the next phase, for the next assignment. In the next assignment, in the next table at the right of the first one, we look for the white boxes in here only. So, and penalty costs are calculated for these white boxes. Among these, the highest one is 55 for the second column. So we look for the smallest transportation cost, and it's 0. The box at the rightmost on this column. So now we look at the demands and supply values. Between these two, 200, the demand is the smaller one, so the assignment here is 200. Now we pass on to the next table. Similarly, we look at only white boxes in here. Penalty costs are recalculated, as you can see, and then the assignments are done based on the same procedure. At the last table on the right at the bottom, all assignments are done in here. So we obtained the initial basic feasible solution by the Vogel's method, and the objective value of this basic feasible solution is 146,000. Right after determining the initial solution, the next is testing the optimality of this solution. Modified distribution method, MODI in short, is a specialized version of the simplex method. We can test the optimality of a basic feasible solution by using MODI. This method requires some steps to be followed. First step is to denote the simplex multipliers UI for each row and VI for each column alongside the transportation table. Second is to writing down the equations UI plus VI equals to Cij. Cij, as you can remember, it is the cost of transportation from from origin I to destination J. These equations must be written down for each basic variable xij. The third step is to set one of the multipliers to 0 and to find the values of other multipliers in the system of equations. System of equations is the one that we obtained in the previous step in here. The fourth step is to calculate the values of Cij minus Ui plus Vi for each non-basic variable. Any of these values is greater than or equal to 0, then the solution is optimal. If not, the non-basic variable that has the most negative value is the entering variable. And this is the solution method for transportation models. Now we can pass on to the next model, that is assignment model. An assignment model can be considered as a special case of the transportation model. The assignment model has the origin locations from where a single unit can be transported to a dedicated destination and vice versa. The solution method of the assignment model is called the Hungarian method. The method begins with the matrix for the cost of assignments. Here we have a cost matrix. On the left, there are jobs to be assigned. At the top, we have workers. These are the assignees. And the costs of assignments can be considered as the wages for these jobs for specific workers. Here, the first step is to identify the smallest value for each row for the cost matrix. Here, for the first row, the smallest value among these is 160. For the second row, it is 120, and so on. Then we subtract each row's smallest value from all the costs in the respective row. For the first row, we subtract this value from these costs, and it yields this one. For the second row, for instance, for the first box of the second row, 140 minus 120 yields 20. For the second row, it is 22. For the last two rows, it is 120 minus 120, and it yields 0 for these boxes on this column. The same are done for the remaining rows, and we obtain now another matrix. This is an alternate matrix by the first step. Here the second step is to identify the smallest value of each column for this altered matrix. Then we subtract each column's smallest value from all the costs in the respective column. For the first column, 40 minus 20 is 20. 20 minus 20 is 0 in here. 180 minus 20 it is 160. And for the final box in the first column is 80 minus 20, and it yields 60. As the subtraction will be 0 for the remaining columns, there is nothing going to be changed for these columns as the subtraction is the 0. So we have this column, this matrix for the second step. In the third step, we mark the columns and the rows that have a box with 0 value. Here you can see these are marked with gray color in here. These are the 0 values, and we have 3 columns or rows in total, which is painted in gray. If the number of the gray colored rows and columns is equal to n, and n is the number of the origins or the destinations, for the specific problem n equals to 4, but we have 3 in here, so this solution is not optimum. It must be 4, then it will be the optimum. However, we have 3, so this is not the optimum one. So we pass on to the next step. It is to determine the smallest value among the white boxes. The smallest value of this boxes is 20. Then we subtract this value from the white boxes here and add this at the same value, which is 20. We add the same value to the intersections of the gray rows and the gray columns. Now the number of the gray rows, gray columns is equal to 4, as you can see in this table. 1, 2, 3, and 4. So that means we have reached the optimum. Finally, we identify the optimal solution by the coordinates of these 0 values elements in the final cost matrix. This is the final cost matrix, and we look for the 0 values, and these are the boxes to be assigned the jobs to workers. And this is the assignment table, and these are the cost of the assignments. In other words, these are the wages. The objective value of this basic feasible solution, in other words, the total cost of the assignments, is 500. Now we have solved the assignment model by the Hungarian method. And this is all for this video. I highly recommend you to read this chapter on your coursebook. Hope to see you in the next videos.